In this experiment, you will synthesize the compound tin-4 tetraiodide. This reaction involves two elements, tin, which is a metal, and iodine, which is a nonmetal. The product, SnI4, is a bright orange solid that precipitates from the reaction mixture upon cooling to room temperature. Tin is a member of the group 14 elements and exhibits both +2 and +4 oxidation numbers. The elements in column 14 include carbon, silicon, germanium, tin, lead, and the last member, ununquadium, which is unstable and radioactive. Carbon, silicon, and germanium exhibit -4 and +4 oxidation states, whereas tin and lead's common oxidation states are +2 and +4. The increasing metallic behavior is apparent in this trend of prevalent positive oxidation numbers going down column 14. This reaction verifies the metallic characteristic of tin, since it reacts with iodine, a nonmetal, to form the covalent compound SnI4. A tetrahedral structure of iodine atoms bonded to a central tin atom would be predicted for SnI4 using the valence shell electron pair repulsion model. All elements in group 14 have 4 electrons in the valence level, 2 in the s subshell and 2 in the p subshell. The more metallic elements in group 14, tin and lead, tend to lose either 2 or 4 electrons, resulting in a +2 or +4 charge respectively. By losing the 2p electrons, there are no unpaired electrons in the n = 5 level, and if the 2s electrons are also lost, the resulting outer level n = 4 is filled, giving a very stable electron configuration. The reaction between tin and iodine involves a transfer of electrons. In this reaction, the tin loses 4 electrons and is oxidized to +4, whereas each iodine atom accepts a single electron and is reduced to the iodide ion having a -1 charge. Combining the two half reactions gives a balanced chemical equation where a single mole of tin reacts with 2 moles of the diatomic iodine molecule. To ensure that the tin reacts, it has been washed with concentrated hydrochloric acid to remove any oxide coating that might have formed on the tin surface. The round bottom flask shown here contains the reaction mixture of tin metal and iodine dissolved in dichloromethane, or CH2Cl2. This mixture is gently refluxed using a water bath. The water condenser attached to the round bottom flask prevents loss of dichloromethane during reflux, with the heat from the water bath promoting formation of the product SnI4. The SnI4 product is soluble in CH2Cl2. A good yield during this reaction may result in formation of some orange SnI4 on the walls of the round bottom flask. By converting the mass of I2 and the mass of tin into moles and using the balanced equation for this reaction on the previous slide, the limiting reagent can be determined. The orange product SnI4 is soluble in CH2Cl2. When you have finished heating the reaction mixture, you will separate the condenser from the round bottom flask. Then you will decant the CH2Cl2 solution containing the dissolved SnI4 into a 50 ml beaker, leaving behind in the round bottom flask any unreacted tin or iodine or precipitated product. It is important in this step to only pour liquid from the round bottom into the beaker. The beaker containing the SnI4 dissolved in CH2Cl2 is put in an ice bath and allowed to cool for 10 to 15 minutes. The SnI4 crystallizes and is collected on a Buchner funnel by vacuum filtration. If any unreacted tin is in the crystallized product, then the product must be redissolved in the minimum amount of hot CH2Cl2. Then the hot CH2Cl2 solution containing dissolved product is decanted, leaving behind the unreacted tin. This CH2Cl2 solution is then put in an ice bath to recrystallize the product, with the SnI4 collected by vacuum filtration. Your TA can help you remove any solid I2 that has contaminated your product. Product characterization is completed using melting point and % yield calculation. To calculate the percent yield, you must determine the limiting reagent, and using the balanced equation for this reaction, determine the theoretical yield. Your actual yield will be the mass of your dried product at the end of this synthesis. The percent yield calculation can be completed using either moles or grams. A minimal amount of acetone should be used to clean your glassware. Any rinsing from cleaning glassware or remaining reaction mixture from your round bottom flask will be collected in a common waste bottle. A final washing of your glassware with soap and water is recommended.